I appreciate you guys being here. That's all. That's all. It's always much better knowing that people are tuned in and listening and watching and seeing you guys. So that's good. Okay. All right. We are continuing to talk about Monte Carlo integration. We'll see how long it takes me to get through this lecture. Maybe I need to add more slides. Maybe this is okay. So we left off on Monday. We talked about some applications of Monte Carlo integration. And one of them is that we can estimate the integral of a function on some closed interval, okay? And you know, one of the situations here is you might have an integral and it's going to be difficult to integrate directly, and but you want to evaluate, you know, what is the value of this definite integral here. And so we said that we can take advantage of the fact that if you just think about what's the average value of a function, right? What's the average value of a function over some interval a to b? One way to calculate that is you take the integral of it and you divide by the width of that interval. Okay, so we can say the average value is going to be equal to this. And so if we think of that, then we can rewrite this average by bringing in 1 over b minus a into the function. And now we have the integral from a to b of h of x times 1 over b minus a. Okay, and 1 over b minus a is going to be the PDF of a uniform distribution, the f of x, PDF of a uniform distribution on the interval a to b. Okay, and so because we have just arbitrary function multiplied by a PDF, we can express this integral as the expectation of the function h of x, where x comes from the PDFF. All right. Is that okay? So we often see this kind of relationship here. The integral of h of x times f of x dx is expressed as the expectation of h of x, where x is a random variable coming from f. Okay, and if we know this, then we can get back the original value of the integral. Okay, because we know this thing is approximately equal to this, is equal to this thing, and therefore the integral here is just going to be b minus a times our Monte Carlo estimate of h bar then. Okay, and so so this is the process to estimate an integral of any kind of function, is that you're going to generate values from the uniform distribution. You're going to compute h of x for all of those values that you've generated from the uniform. You're going to just take the sample mean of all of that, you know, after you apply the function h of x to all those values. You can take the sample mean, and then if you want to estimate the size of the integral, or the value of the integral, you multiply it by the width of that uniform distribution. You multiply it by b minus a. Okay, so I think I hope that's okay and that's straightforward enough. What did I do? Oh, okay. Let me give you your first quiz answer for today. First quiz answer is D. D as in dog. D as in dog is your first quiz answer. Okay, so let's take a look at this function, and we're going to just try to estimate the integral via Monte Carlo integration. All right, and so what we want to do is we want to kind of find the average value of the function from 0 to 1, and then we're going to multiply by the width of the interval. Okay, so and then if you compute it kind of analytically, you get 0.9652. And so we're hoping to find something similar to that. Okay, so here's this is what you get if you plot the function. It looks like this, and we want to evaluate basically the area underneath this squiggly line here. And so this is how I did it. I generated 100,000 numbers, 10 to the 5, and then we generate a bunch of numbers from the random uniform. I apply the function h to all of those random uniform values, right? So h is just cosine of 50x sine of 20x squared, which is what we said this function is. Okay, so I have the function plugged in program there, and then so that gives me all of the h of x values here. And what's the mean? The mean I get is 0.9668. Okay, so it's a little bit off. The true value is 0.965. So we're off by 0.2 of a percentage point, but I feel pretty good about this. Okay, so this is what we have. That's going to be our h bar, and then and the width of the interval, because I just generated from 0 to 1, the width of that interval is 1. So the value of the integral itself is also this. Okay, now if the width of the interval was much wider, then the value of the integral would be something greater. All right, is that okay? So far, so good. Okay, so let me actually pull up a couple slides from Monday's lecture. Okay, so on Monday we talked about estimating the variance of this estimate. So we have this sample mean of h bar sub n, and we said, what is the variance of this thing? Well, the variance of it is going to be 1 over n of the variance of h of x, and we said we can estimate that variance. So this is again, this is from Monday's lecture. We said we can estimate it using this 1 over n times basically the expectation of this. Okay, and so the overall the variance can be estimated by this quantity, 1 over n squared times the sum of h of x j, the sum of the h of x j's from j equal to 1 to n minus h bar sub n. Okay, so whatever our current estimate is, we're going to take all of those values, square them up, and this will give us an estimate of the variance. Okay, and so so I'm going to compute basically a cumulative value of h bar sub n. Okay, so this is this value h bar sub n 0.96686. That's my mean after 100,000 values. Okay, after 10 to the 5, after 100,000 values, this is the mean I get. But what I'm going to do is I kind of want to know, like, what is the mean that I had after 3 values? What's the mean that I had after 4 values? What's the mean I had after 5 or 6 or 7, all the way up to n? So this is going to become a vector of length. Well, it got too big, or there's just too many values if I did the full 100,000. So I just did 10,000. Okay, so this is basically, I'm just going to look at the first 10,000 values and calculate kind of the cumulative mean. So this is going to be a vector of 10,000. So the first will be the just the first value, and then the next value will be the average of the first 2, and then the next value will be the average of the first 3. The next value will be the average of the first 4, and so on and so forth. And similarly, I'm going to calculate basically the running variance, okay, using this, but I'm going to compute it for j equals 1, j equals 2, j equals 3, all the way up to 10,000. Okay, so so I created a function. I called it variance underscore m, but I guess I could have plugged in j here. And basically, it's just going to take the h of x values, which is what we've got here, and then we're going to subtract off the mean, the h bar sub n, up to that current value m. Okay, and then we're going to square that and divide by, whatever m squared it is. Okay, so it's just, I'm just programming this function as kind of a variance, but it's kind of like a running variance. Okay, and then in order to kind of compute this for all of the values, I'm going to run an apply function, and so I just kind of create a matrix of 1 through n, 1 through 10,000, and then and going down the column, we're going to compute the variance, this function. We're going to apply it here, and it's going to go through all of these values, and it's going to just kind of get a running variance. So in the beginning, when there's very few observations, your estimate of the variance is going to be big, but then as the number of observations increase, this value of the variance is going to get smaller and smaller and smaller. Okay, does that kind of make sense? The function, like why I bothered writing all of this stuff here, and then the standard error of our estimate, the standard error of basically your sample mean is going to be the square root of this variance thing. Okay, and this is basically, all of this is informed by kind of the work that we did on Monday using these slides here. And I think so. I refer to this. I said see slide 27 of lecture 2-1. So if you're going, when you go reviewing your notes, I hope, and you're wondering where this is coming from, it's coming from here. Okay, and then, so now that I have my standard error, I can kind of take our H bar, our running sample mean, which starts off with, the sample mean of just kind of like 1 or 2 or 3 observations. And then as the number of samples increases, it's going to kind of become steady. And then I'm going to add kind of 95% confidence bands using kind of 1.96 times the standard error and minus 1.96 times the standard error. Okay, so this is just kind of your 95% confidence interval. And this is basically saying that, I'm 95% confident that, because this is an estimate, right? H bar sub n. I guess I don't have it on here, but this thing is an estimate of this thing, right? So this is the true mean that we want to know. And basically we've got a sample mean. And so this is an estimate of this. And so we're saying, I'm 95% confident that this true value is going to be within plus or minus 1.96 standard errors of this quantity. Okay, and this is what the plot looks like. So just going off of the first 10,000 iterations, okay, and I think I ended up computing around 100,000. We can say, based on what we've seen so far, I'm 95% confident that this true value, which remains unknown to us, this true value is, between this top and bottom of the blue line. Okay, and so we could see that in the beginning, there's a lot of variation because the standard error is huge, because there's only been a few observations so far. But then as we get more and more observations, and here I only plotted 10,000, because if I did 100,000, then the graph gets really, really, really boring. It just looks like this part. I guess the interesting part is in the beginning where there's a little bit more variance. That part just gets squished down to be very narrow, and then the rest of the graph kind of just looks like three stripes of blue, black, and blue going straight across. So the full 100,000 is a very boring graph. Not that this is super exciting, but it looks like this. And in the textbook, this graph also appears. The textbook did something different for the calculation of its confidence bands, and to be honest, I don't know if I fully agree with the way it calculated its confidence bands. I feel like what we did here makes sense to me. So anyway, that is that's estimating the kind of the value of some integral function based on kind of using Monte Carlo integration here. Okay. All right. So far, so good, I hope. Okay. All right. Here's another example of Monte Carlo integration. And this is a tiny bit of a silly example because basically I'm solving a problem that has already been solved. That, you know, this is not actually necessary, but it's still a kind of an interesting exploration, and we can take a look here. Okay, so you know, what if we want to estimate the cumulative distribution function of the normal distribution, right? So if you need the CDF of the normal distribution, technically we can do this using P norm, right? So if you have P norm is gives us the CDF of the standard normal. I don't know if you knew this, but P norm is technically an approximation, okay? It's a very good approximation. It's accurate up to 16 digits, but it's not accurate beyond that. But that's good enough for us because using floating point numbers on the computer, floating point numbers on the computer can only represent up to 16 digits anyway. So if you have a function that's accurate up to 16 digits, but is not accurate beyond that, it doesn't really matter, right? Because your computer can't even represent that. So P norm is an approximation, right? Just like when you type in pi on the computer, it's an approximation, right? Pi technically goes on to an infinite number of digits, but we just have like the first 16 digits in, you know, floating point arithmetic, and that's good enough for us. You know, I wonder what's going to happen in the future, because I imagine we're going to be able to store more than 16 digits, and maybe things will get more complicated. You know, back in the 60s when they were planning out Apollo missions to the moon and stuff, they used like slide rulers because, I mean, of course they had calculators as well, but for a lot of computations they used slide rulers, which were accurate probably to like 5 or 6, you know, 4 or 5 decimal places. But that was good enough. That was also good enough. So it seems a little crazy to us now that we have access to 16 digits so easily. But anyway, okay. So this is what the this is the normal PDF over here, and to get the normal CDF, you integrate from negative infinity to x. Oh, what is a slide ruler? Oh my goodness, we got to take a small detour. A slide ruler is the physical representation of a logarithm. Okay, so in a log, it turns products into sums, right? And so what you have with a slide rule is basically, if you want to take the product of, say, let's say you want to multiply 2 times 3, okay? These numbers are printed in log scale, okay? And so when you do when you do 2 times 3 and you represent them with logs, you get the log of 2 plus the log of 3. So you get the log of 2, which goes from 1 to 2, and then you add the log of 3, okay? And that will give you the log of 6. I mean, so the log of 2 plus the log of 3. So, and that equals basically when you convert things using logs, addition becomes multiplication. So 2 times 3 is equal to 6, and you can take log of 2 plus log of 3, and that will equal log of 6. And you can do multiplication this way as well. So so anyway, it's kind of neat, right? The log of, and you can see log of, if you do log of 2 plus log of 4, it takes you to 8 log of, any of this stuff. So so the slide rule is, physical representation of logarithms, and it allows you to do products of complicated things, and you can get fairly precise because your slide ruler will have this kind of like very thin line and stuff. Anyway, it's kind of cool. Okay. Anyway, so we're not that's an aside. Okay. So let's say we just want to approximate the normal CDF, right? So the CDF is the integral from -infinity up to x of the normal PDF dt, okay? And it's basically equal to, the probability that some random normal value, standard normal, random normal value z is less than some arbitrary value x, okay? And so we could do this with Monte Carlo integration. So let's say you have a function I, that's an indicator function. And what we're going to do is we're going to just put in z less than or equal to x. And this is equal to 1 if z is less than x. And it's 0 for any values of z that are greater than x, okay? And so if we say, well, what's the expected value of this function? Okay, the expected value of I here is going to be 1, basically the value times the probability of this thing, and 0 times the probability of this thing, okay? And that just becomes equal to the probability of z less than or equal to x. And that is exactly equal to the cumulative distribution function, right? So f of x is equal to the probability that z is less than or equal to x. And we have shown that the probability that z is less than or equal to x is equal to the expectation of I. All right, and so the CDF f of x is expressed as an expectation here. These two things are equal. And so, using Monte Carlo integration, where we said, we can express expectations as we can approximate this. We can just let h of x, all right, be equal to this, right? So here's kind of in Monte Carlo integration, if we just let the function h of x equal this I, then the expectation of this, the expectation of I, will just be equal to our CDF, okay? And so it's easy. We're going to let h of x equal I of this, and to compute the normal CDF, and it seems really silly once we go through all of this, but basically we're going to generate a bunch of random values from the standard normal distribution, okay? So we're going to use R norm on the computer or some function like that, okay? And then we're going to compute is z less than or equal to x, okay? And we're either going to get ones or zeros. And then and we estimate the CDF by just taking the mean of the ones and the zeros, okay? And this is very easy on the computer because if you just make a comparison on the computer, you're going to get a logical vector of trues and falses, and then you can just ask for the mean of a logical vector, and it's automatically going to convert everything to ones and zeros, like an indicator function. So it's quite nice, okay? And this method will actually generate any CDF of any random variable, as long as you're able to sample from the distribution. So here we're assuming we can sample from the normal distribution, that we can generate random normal values, which we're able to on the computer using R norm. And if you can generate values from any probability distribution, random values from it, then you can estimate its CDF in this same fashion. And the reason why it works is that if we kind of take a look at it, okay, the answer to this, okay, is basically a Bernoulli random variable where p is equal to whatever f of x is, okay? Being a 1 or 0 is basically a Bernoulli random variable, and the probability of success is the probability that z is less than x, okay? And therefore, when you look at kind of this estimator, this is basically just the sample proportion of successes in n trials. So if you do like a million trials, h bar is just the sample proportion. So so here I'm creating a huge table of all of these things. I mean, it's really it seems kind of silly if I do this, but I'll go ahead and just show you. I can just do, I'm going to do z is, let's do r norm of 10 to the 8. Okay, so we're going to generate a whole bunch of values of z, and then let's say we want to estimate is, you know, what's, we're going to estimate p norm of, say, 1.28. Okay, and so all I'm going to do is I'm going to do z less than 1.28. Okay, and we're going to ask basically what's the mean of that. So z less than 1.28, this is going to be a logical vector of true falses, and I could say what's the mean of this, and r comes back. I hope you guys can see this. R comes back and it says the mean of that is 0.8997, right? And we can compare that to the true value of p norm of 1.28, and they come out pretty close, right? 0.8997638. This is my estimate based on 100 million random normal values, and this is the true value. P norm of 1.28 is 0.8997278. Okay, we can just kind of estimate any other value. We can say what's P norm of, say, negative 1.645, right? Okay, and here I get something around 5%, whereas P norm of negative 1.645 technically is a little bit less than that, 0.04998. Okay, I'm just kind of plugging in your standard. And so we're just asking basically what proportion of z is, say, less than 0. So how many of my 100 million values, how many came out to be less than 0? Well, I guess about half of them, 50,751,000, whereas, you know, the true value for p norm should be exactly 0.5. Okay, so p norm of 0 is exactly 0.5, and if you do a 100 million random normal values, in my situation, I got 50,751,000 I'm sorry, 50,007,510 came out to be less than 0. Okay, and so so here, just to kind of generate the following table, I generated 100 million random normal values, and then I calculated kind of boundaries for Q norm 0.5, 0.75, 0.8, 0.9, 0.95, 99, 999, and 9999. This is taken from the textbook, and then what we're going to do is I want to try this. What I'm trying to show is that on the next slide is how our estimates improve if I use 10 to the squared 100 random values versus 1,000 versus 10,000, 100,000, or a million, 10 million, or 100 million random normal values. How well do our estimates improve by increasing the number of samples by a factor of 10? Okay, and then so we're going to kind of take some of these values of x here, and then from there we're going to ask how many are less than whatever boundary we've chosen, and then we're going to compute the mean of that. Okay, and so this is a table, and so you know, p norm of 0, we know that the true value, the actual value, is 0.5, and how good is our guess when we use 100 values? With 100 values, we got 52, out of 100 to be less than 0. So my guess is a little bit off, okay? With 1,000 values, 490. With 10,000, 4,992. So my guesses are improving. At 100,000 values, we got basically 50,082. So about, this value gets closer to 0.5. With 1,000,000 values, this is the proportion that was less than 0. With 10 million and with 100 million, this is the proportion that came out less than 0. Okay, so these numbers get closer and closer to 0.5, and we can see how all of these things, all of these values in general get closer and closer to their true values as the number of random values increase. Okay, and so so here the actual value is 0.999, and with 100 we just got 1,000. When and so these estimates improve as we take more and more random samples. Okay, and that's and so there's kind of this question of how many values do we need, right? So generating 100 million random normal values is computationally expensive. Even with a fast computer, it takes a moment to generate 100,000 values, right? And so the question, will this converge linearly, or can we make it converge faster? So with Monte Carlo, its kind of rate of convergence is going to be 1 over the square root of n. Okay, and so so if you take a look at this, right, if we do a little bit of math here, all right, and we say the normal CDF, okay, or just any CDF really, can be expressed as a sample of proportion of successes. Okay, and so if you think about, what's your sample proportion? So if you think back to stats 10, what's the variance of a sample proportion? It's p times 1 minus p over n, right? Or your standard error is the square root of p times 1 minus p over n. And so the variance of a sample proportion here, in our case, the sample proportion is not p, but it's f hat. It's going to be f hat times 1 minus f hat over n. Okay, so I don't know. Do we remember that? Sample proportion, p times 1 minus p over n. Okay, so that's our variance. And so the variance is going to be have it kind of its maximum value when the p hat is equal to 0.5. Okay, and other values of p hat will end up with a smaller variance. So if you're kind of just thinking of like what's a conservative estimate for the variance, kind of if you kind of guess that your variance is going to be the biggest, it's going to be 1 over 4n. Okay, if you put in 0.5 times 0.5, you're going to get 0.25 over n. And so you get 1 over 4n, and if you take the square root of that, your standard error is going to be 1/2, 1 over 2 square root of n. Okay, and so the kind of the amount of improvement improves, inversely to the square root of n, right? And that kind of aligns with, I think, what you learned in your intro stats class, is that if you want your standard error to cut in half, you need to get a sample that's 4 times as big, right? And if you want your standard error to go down by a factor of 10, you need to increase your sample size by a factor of 100, okay? And so let's say we want to be 95% confident that our estimate is accurate to 4 decimal places, okay? Basically, we want then 1.96, or 2 times our standard error, to be less than 10 to the negative 4 to be accurate to 4 decimal places. So if you want to be 95% confident that your value is accurate to 4 decimal places, then to kind of make sure your standard error is this small, you need 10 to the 8, okay? So you basically need 100 million. And if you want to be accurate to 5 decimal places, then you need 10 to the 10, which is 10 billion. Okay, so that's a lot of numbers if you want to be accurate to 5 decimal places. Okay, and so there's a bit of a trade-off. but that's what we have. So the accuracy kind of converges at a rate of 1 over the square root of n there. All right. Is that okay? Let me give you another quiz answer. Second quiz answer for today is C as in cat. C as in cat is the second quiz answer. C as in cat. Okay. How do we feel about this? Is this feeling okay? All right. Okay, so I'm going to introduce our next topic, which is called importance sampling, and we'll cover this today and Friday. We'll spend a good portion on Friday. I'll probably release your second homework assignment today as well, and I'll set a due date for that in the future. Okay, so what is importance sampling? So first of all, I don't really like this name, importance sampling. I think a better name would be like weighted Monte Carlo integration. So we've talked about Monte Carlo integration, and this is what we've established, right? We said if you want to know the expectation of this function applied to x, where x comes from this PDF f, then this is how we would estimate it. Okay, we would or this expectation is equal to this integral, and we would estimate this integral by drawing random values of x from f, and we take the sample mean. Okay, and for Monte Carlo integration, it depends on our ability to produce random samples from the PDF f of x. Okay, and so when we wanted to do it, we assumed we could produce values from the random uniform, or we could produce values from the normal distribution, or one of our earlier examples, we were producing values from the beta distribution. Okay, and so we're assuming we can produce values from these PDFs, and so far all of our probability distributions have been built into R, right? So this is what we've been doing so far, is that we've been generating random values by using R's built-in distribution functions, right? So we've been using random uniform, random normal, random beta. That's what we've done. And there's a whole bunch more probability distributions built into R, such as the gamma, exponential, chi-squared, F, Poisson, binomial, so on and so forth. So I think, where do you learn about all of your probability distributions? Is that 100B or 100A? A little bit of both. You learn how the, F is the ratio of what is it? T distributed random variables and stuff like that. Okay, so anyway, so we can do this, right? And we might come across some kind of PDF that's not built into the computer, right? So technically, any function, as long as it meets 2 criteria, qualifies as a PDF, okay? And the 2 criteria is that it cannot be negative anywhere, and if you integrate it, it integrates to 1, okay? So you can take any function, as long as it's a non-negative function, everywhere, as long as it's non-negative everywhere, and as long as it integrates to 1, or I guess if it's discrete, if it sums to 1, then that can count as a PDF or a PMF, okay? And we might not have every function built into R. So what do you do if we can't sample from that PDF f of x directly? Okay, so what do we do in that case? All right, so next week we will talk about strategies for generating random variables from different distributions. So we'll talk about, how can we, if I get a new f of x and it's not one of these things where, R already has it built in, or we could, next week we'll probably just talk about, how might some of these things work. We're going to talk about how to generate random values from different distributions or different functions. That's going to be next week. Okay. But the other option is we can perform importance sampling. Okay, and so I'm going to just kind of introduce this idea here, and then we'll delve into it on Friday. Okay, and so here's our goal. Again, our goal is we want to estimate this thing, but the problem is we don't know how to generate values from f, right? We want to estimate the value of this function h of x, and x comes from this random distribution f, but we don't know how to generate values from f. So I can't do my old strategy of just generating a bunch of values from f and then applying h and taking the mean. So instead we're going to say, well, I don't know how to generate values from f, but I do know how to generate values from g, okay? And g is just a completely different probability distribution. So someone says, you know, I want you to make me I don't know, make me a chocolate cake. And you say, well, I don't know how to make a chocolate cake, but I do know how to make I don't know, pie. So that's what we're going to do. Okay, we're just going to go ahead and we're going to generate values from something entirely different. All right, and right now the only requirement is that the support of f has to be fully contained within the support of g. Okay, that is, g is going to be greater than 0 wherever f is greater than 0. So if f is greater than 0, then g is also greater than 0. You can have spots where f is equal to 0 and g is greater than 0. That's fine. Okay, but the support of f has to be contained entirely within the support of g. That's the only difference. Okay. And this is what we're going to do. We're going to re-express this function or this expectation as an expectation in terms of g. Okay, so so all I'm doing is I'm going to just write this out as the integral that it's equal to. Okay, and then I'm going to multiply by g of x over g of x. Okay, so this is, we can do that. And if I just rearrange, if I just move this over, okay, now I've got h of x times f of x divided by g of x, and I can kind of just group this together, right? And so this becomes kind of the new function in here, right? And so again, the key is that g of x, you know, is not going to be 0 any place where f of x is 0, okay, or is greater than 0, and f of x is 0 for anything that where it's outside of this domain here or the support here. And now this thing, so we can just pretend that this is just some other newly named function here. This thing is going to become the expectation under g of this entire mess here. Okay, so now, so here's the expectation of the function h of x, where x is generated by f, is equivalent to the expectation of this mess of functions where x is generated by g. Okay, does support mean the area? Yeah, support is kind of the, I guess, the region where the function is greater than 0. So it's the region where the function is greater than 0. So it's wherever the PDF is greater than 0, that's going to be the support. So the normal distribution has infinite support going from negative infinity to positive infinity because the function is asymptotically approaches 0, but never equal to 0. Whereas the beta distribution, the support goes from 0 to 1. Anything outside of that interval 0 to 1 is equal to 0. Anything inside of 0 to 1 is greater than 0. Okay, so this is our strategy, and we'll talk about this because it seems kind of crazy that this would even work, but it does. Okay, that's yeah. So we'll talk further about this, and so I'll copy the slide over, and we'll get into important sampling. But basically, this problem, even if you want to estimate this and you don't know how to generate values from F, we can get around it. We can do a importance sampling. I think weighted Monte Carlo integration is a better name for it, but nobody calls it that. It's always called importance sampling. And we can do that, right? And then next week, we'll talk about this other strategy for dealing with it, which is generate the values from f of x directly and using a different strategy here. Okay, we'll end here. Let me give you the last quiz answer. Last quiz answer is E as in elephant. E as in elephant. That's our last quiz answer for today. And then on Friday we'll continue discussing importance sampling. And then I'll probably get another homework assignment posted soon. So, okay. All right, we'll see you then.